So I could make a simple prism. I could have a ray of light coming in here, try to make it look like as if it were the parallel rays case, if they're all coming in horizontally. Then I get some bending here, and I get some more bending coming out. Again, each one of these bends here is based on Snell's law, which I just covered. I'm not doing the exact algebra for this example, I'm just drawing a kind of abstract picture. And so this is, you know, just a simple triangular shape. You can imagine that it just extends the same way in what we've been calling the z direction. So it's cylindrical in the z direction, if you like, and has a triangular cross section. So some kind of prism, and I could make the upside down version of that. May look something like this, right? So that's the behavior of a single ray going through a prism where there's medium 1, then you go into medium 2, let's say, and then you come back to medium 1. So this is essentially the principle that's going to be applied in a continuous fashion across an entire lens. So if I make a simple spherical lens, I get something like the following. Soon I'm going to stop drawing pictures and switch to slides because it gets complicated to trace all of these rays of light, but this will be one of the last pictures. Let's say that I try drawing myself. So these should look like circular arcs, and there's really another dimension to where these are spherical now. So these are spherical caps, just like the way lenses look that you're familiar with. Whereas this was supposed to be just the same outward, so there's no curvature. I have my, let's see, I have a central axis for this, a kind of axis of symmetry. And I have rays of light coming in, and I'm going to assume this thing that I told you was fictitious, which is there are parallel rays coming in. And they're only fictitious if you live in a world with no mirrors or lenses, so I guess we could have produced it through some other means, but if it came from a point light source, then this is impossible but a reasonable approximation. So we have these parallel rays coming in, and when you think about the behavior of these, it's like when it comes in and when it comes out, it's like having a slice of a prism, right? So that's the kind of thing to think about. It's a slice of a prism, and if these rays are coming in at a different angle, then I guess it'll be a different slice of a prism, right? So it represents all of that somehow. It's this prism bending effect, but manifesting itself in very localized ways depending on exactly what the curvature is here, right? This is not a curved surface, so you can predict what's going to happen all the way up and down. It's going to look the same, but because this is curved, the bending is going to depend on where you're at along the curve here. So as it goes through the lens, we end up with, let me draw a another axis here, which should be the center of the lens. Not very good at straight lines today. You ever have a bad straight line day? You know, so what's going to happen is, in this lens, is that the effect of refraction is going to cause these rays to bend inward to start to converge. And if we make a simple spherical lens, they will converge to a point somewhere. Let me just invent the location of that here. They will converge to some point, and this point is called the focal point. Whenever you hear the term focal point, remember that that corresponds to what the lens would do for parallel rays, right? And I guess I have to start to draw what happens to these rays as they come through. It's going to be very difficult for me, but let me I'm going to do my best here. I won't draw all of them. Of course, at the central part of the axis, it just goes straight through without any bending, right? Something like that. I guess I have to match these pictures a bit here. Well, I'm not really sure. I'm probably not following the same rays, but Get the idea, because of course these come from somewhere inside the lens. So I don't think I have my arrows to the left matching exactly the ones to the right, but I think you understand the idea. I'll start providing some machine drawn pictures or more correctly drawn pictures in just a bit. So that's the focal point that they all converge to, and this distance here is called the focal length. So that's how we think of a simple lens, in this case as a kind of engineered device that takes parallel rays and makes them all converge to a point somewhere. They don't stop at that point, they keep going, right? So it could also continue onward. They meet at that point, but there's nothing to stop them from continuing onward unless you put something here. What might you put here, like a screen perhaps? I don't know. So if you put something here, then the light will be focused on whatever you put here. Remember that there's an interpretation in terms of waves. Draw the waves in blue here. So we had parallel waves coming in, and now after they get through here they're getting curved in some way. Right? So that's another way to look at it, is when the rays are being forced to converge through the lens, you're introducing curvature now to the wavefronts. So if you were going to play everything in reverse, this starts to look like a point light source and the waves are propagating out like this now. Isn't that interesting? So you get this strange effect. All right. One more. I'm kind of afraid to draw the picture. Let me see if I can just superimpose it on this. Let's suppose I have rays coming in at an angle, but they're still parallel rays. So let me draw rays coming in at some angle. I realize it's getting pretty cluttered now. So I just want to point out that just because they're parallel rays, it doesn't mean that they come in perpendicularly, right? Right? The rays are parallel, but they could be coming in at an angle, because I could imagine that there's this light source that's off at infinity, but it could be up really high, right? So if I'm sitting out here in the open air theater watching a movie on the big screen, I could be, and imagine that screen is gigantic and it's really far away. Maybe it's 10 kilometers away and it's enormous and it's a clear day and I can watch the movie like that. There's still going to be the top part. The rays are going to come in, they're almost parallel, but they're going to be coming in at an angle, right? So in this case, for an ideal spherical lens, they will still converge, but they will converge somewhere else along this line. So there may be these rays coming in that correspond to some distant feature or object. The wavefronts have spread out so much that the curvature the radius has turned out to be essentially infinity, so that when we have these parallel wavefronts coming in, we have straight lines, we have parallel lines, which is represented by the pink here, so that everything comes in and we end up with the focal point being, I'm just going to draw it in some arbitrary place down here somewhere. The important thing to note, is that they converge, and they converge to another place along what is called the focal plane, right? I think when I was talking about curvature going up and down, let's see, curvature 0 means what? Straight line, but the radius of curvature would be infinite there, right? So I got to be very careful. I think that's part of the confusion in my speech just a little bit ago. I think that so I wanted to say that the curvature of the wavefronts is approaching 0, but the radius of curvature would be approaching infinity. So make sure I've said the right things at different times. So it's just those two are inverses of each other, even though the names are very similar. All right. So there are simple formulas for determining the focal length of a simple spherical lens, and so I want to go into some pictures of that, explain some optical properties and things. We'll go back and forth between the board and some pictures. So this should correspond pretty closely to the picture that I've drawn, and oops, don't do that. Notice that we have the focal length as I've drawn it. There's also a thickness of the lens d here. And note that we have two different radii, R1 and R2, that correspond to the curvature of the one of them corresponds to the place where the light first hits, which it looks like R2 in this case, and then there's R1. Oh gosh darn it, sorry, hold on a minute. The R1 corresponds to a circular disk, and that's the place where the light first hits, and then R2 corresponds to the place where the light hits second. But note that the center of the circle is before the light hits for the second circle, and it's after for the first circle. So to determine the focal point, we have the following: the lens makers equation. So 1 over the focal length is equal to let's say N2 minus N1. I'm writing it in a little more general form than I have in my notes here, but it should be okay. 1 over R1 minus 1 over R2 plus N minus 1. Nope, this is the place where I'm doing it a little more generally. N2 minus N1 D divided by N2 N1 R1 R2. And then for let's see, N1 is the index of refraction let's say outside of the lens, make it very clear, the ambient, the air outside of the lens, so outside the lens. Usually we mean air, and usually N1 is approximately equal to 1. But you can put your lenses under water and it will do something different, right? It'll behave in a different way. So this is the index of refraction for the lens material. There's a simple approximation that's often used to this, and I will write that here. It's called the thin lens approximation. This is much more common now after this approximation, where we get rid of this D parameter. So here we say D is approximately equal to 0, in which case the lens maker's equation simplifies to 1 over F equals N2 minus N1, so it's the difference in refractive indices, 1 over R1 minus 1 over R2. And there's a peculiar sign convention that's used for these R. So normally when you write R in this kind of geometric picture that we have on the display here, in ordinary geometry the R's would always be positive. However, there's a convention here which is for a converging lens, which we've just made. We have a sign convention which is that R1 is greater than 0 and R2 is less than 0. So this is for a converging lens. I'll put lens type here. That's the only kind I've shown you so far for a converging lens. One way to remember that is that the R1 case is positive because you've hit the surface that that circle corresponds to before you hit the center of the circle. And the R2 case is backwards. It's you've hit the rays of light that are coming into the lens have hit the center of the circle before they actually hit the surface. So in other words, R1 corresponds to the case of a front side, which is an entrance, and R2 corresponds to the case of an exit. So so these are for the converging lenses, it ends up giving you these signs. So there's also diverging lenses. If you've seen optics before, it should not be surprising. So there's the diverging case. Where we can make rays of light instead of converging, spread apart. And I'll just mention the sign convention in this case. So R1 in this case is less than 0 and R2 is greater than 0. And so you can directly apply the lens maker's equation in the original form and in the thin lens approximation to determine the focal point. However, notice that if it's diverging, it seems like it should not even make sense to talk about a focal point. I have parallel rays coming in and then they diverge, but you can trace them backwards. That's what these dashed lines correspond to give a kind of, let's say, fictitious focal point, right. So because once these rays spread apart, they'll still all point backwards if you reverse their direction to a common point. So that is called the focal point of a diverging lens. So the diverging lens does not cause focus to happen. It's the opposite of that, but you can just reverse the direction, run everything backwards, and to the left of the lens you end up with the focal point. Right? Questions about that? I want to, let's see, I want to now talk about a very useful representation called diopter, which becomes very handy when combining lenses, talking about optical power, and then I'll give an example of it in terms of the human eye. The human eye is going to be important because it's part of the virtual reality system.